Cool. 952, largest component size by common factor. Given a non-empty array of unique positive integers A, consider the following graph. There are A dot length nodes and nodes labeled A sub 0 to A sub n minus 1. There is an edge from A sub I and A sub j and only if A sub I and A sub j share a common factor greater than 1. Return the size of the largest connected component in the graph. Okay. What does that mean? Okay. I think this is a good practice problem. I mean, I think immediately when you see stuff like connected components, you should think about stuff like union find or something like that, or DFS. I think let's look at the n. Right, n will kind of determine the the issues. Okay, so n being 20,000 is a little bit tricky because a lot of the standard connected components algorithms are going to be v plus e, but e can be up to v squared, right? And in this case, it can certainly be. I mean, this is just GCD, so they could all like be part of the same component, and then you have a full graph, right? Because you can note that everything is transitive in this case. If well, that's not true. Hang on. Yeah, I guess it's not. Well, it's not necessarily transitive, but for connected components, you like there is some transitive closure in this. So in that case, it doesn't really matter. But that also means that yeah. So that, but yeah, the naive algorithm is going to be n squared for that reason. For like any connected components. So the kind of better way to kind of think about it is kind of figure out the graph in a better way. And I think thinking about this, and maybe just some hints, I think immediately when I look at common factor greater than 1, my mind jumps to GCD again, which is something that we talked about earlier. But maybe I think for each number we just calculate all its factors, like to the prime factorization, and then for each number, kind of. So I think the kind of quote unquote the easy naive way to think about it is kind of having each node, and they try to get you to think that way, right? With the pretty pictures, is that each node is the number, but I think actually what you want to do is that each node is a prime factor. So like for example, I think the way I want to think about it, and this one I could do in Java since people keep on requesting Java, but maybe not. Maybe I'll do. Okay, let me write explanation first. For this number, so 4 prime factorization is 2, well 2 times 2 if you want to be. 2, 3, 15 is 3, 5, 35 is 3 and 7, oh sorry, 5 and 7, right? So for that, it means that, what you want to do is that for each of these numbers is actually an edge. In this case, well, 2 is just by 2, but 6 is an edge between 2 and 3, 15 is an edge between 3 and 5, 35 is an edge between 5 and 7, right? So then now you connect them together, and I think that should be good enough to kind of, and then you kind of maybe do a final loop at the end to kind of count out how many are in each component. And then we could do a union find for each number and all the factorizations. I think what is the so the math that I would do, and I'm doing this on a calculator, but I'm showing you what I'm going to do on a calculator to find out the upper bound of the number of primes or number of nodes. Yeah, number of primes that multiply to under 20,000. So then we can kind of do the math on that. Yeah. And probably like the biggest edge, maybe like 2 times 3 times 5 times 7 times 11 and so forth, right? So let's see what that equals to. I'm pulling out my calculator. basically the number of primes such that it's less than 20,000. So actually, this is already greater than 20,000. So that means that the biggest number you're going to have, well, it's roughly just 5 different primes. In this case, oops, what is this equal to? Where's my calculator? So in this case, this is equal to, okay, 2,000. I mean, I guess that's not that important, but what was I going to say about this? Oh, anyway, that part is actually not important. But what that means is that in this case, this number 2310 creates five choose two edges, right? Which is 10 edges. Is that right? That was now 15 edges. So this will create 15 edges on the graph, but that also means that each number at most can have 15 edges and this with 20,000 numbers, yeah, 15 edges each on each number, and for 20,000 numbers, this means it's about 300,000. So 300,000 is the number of edges, right? So now we can do the traditional V plus E thing, because we know that well, V is equal to, I don't know, I guess up to 20, a little bit, like number of primes that are smaller than 20,000. So let's just say half of them. So like, I don't know, you can look that up, but so let's say 10,000 plus 300,000, which is the dominating number. And then we can kind of do a depth of search and then go back and just do the count on whether they believe in the same thing, right? So now we could do a union find, and yeah, cool. All right, actually, I am going to do it in Python just because I've been meaning to practice union finds, to be honest, because like I can do this in depth of search in Java very quickly, but I do want to practice a little bit on union find, something that I was a little bit weaker on or should have done. So yeah. So in this case, let's do. Do we want to do a SIF? I guess it doesn't really matter. Yeah, okay. So yeah. Let's just do a find of x is equal to if p of x is not equal to x, then p of x is equal to find of return p of x. Okay, and then union is just let's just do a naive union. So x is equal to oh well, two numbers, right? P of, or just find of y. I guess they're the same, really. Well, they should be the same after path compression. So these are the union find operators. And then now, for each number, for x in A, let's actually have a prime factorization routine. So what's there? Okay. So for y in range from 2 to x, we could probably do a little smaller than that. Okay, let's just use the while loop. Y is equal to 2, while times y is then x than x. Then if x mod y is equal to 0, that means there's a factor, then let's have a result list. Oops. If this is a factor, can we have a duplicate number? I guess it doesn't really matter. There's only 20,000, maybe. We could actually pre-calculate all the numbers, maybe even 100,000. That's not a big deal. But anyway, yeah, if x is, if this mods, then that's, well, let's insert y, for example, append y, and then while x mod y is equal to 0, we do that. Yeah, eventually you'll, right? Yeah. And then if x is greater than 1, then we just load append.x. And this is a little bit, you know, and this will always be primes, because if it was not, if y is not a prime, then it would have, oh, I need to increment. That would make things easier. And you could do some math of like, if y is equal to, make sure that it's odd numbers. But it's kind of the same logic with the CIF. Maybe yeah, but it's the same logic of the CIF where, you know, if y is not prime, then the prime number before that would have already modded it to 0 or something like that, or already factor it. Yeah. And then now for x in A, what do we want to do for x in A? Oh yeah, so now we get all the factors of prime factor of x, and then now, oh, we have to set up this, and I probably didn't explain it, but P is the parent, which is the union find parent. That's what I call it. There are other ways to go about it. N where n is, oh, actually, and I was a little bit wrong on my math, but by the way, it's roughly right, because it's actually 100,000. I think I said, so maybe some of these changed numbers slightly, but it should be okay. N is equal to, actually 100, well, this is an N, this is just another max number, say, and this is equal to, say, 100,000. Okay. Okay, now we can do, for each pair, let's union them. For, how do I do, okay, whatever, I guess it's fine. For F1 in factors, actually, you don't, I was going to say you could do pairs, but just by definition, you could also just, union with the first number. So I think that's fine, actually. So for F is numbers, let's find a union between F and the first, I guess I could do this, actually. So it doesn't do it with itself. Also, let's just name things a little bit better, not in a rush. Okay, so so yeah, so actually this is, I mean, I didn't say that as part of my thing because there are 15 edges, but you actually, because of it is a connected component, you only need 4 edges. So this is actually even way faster because there's only 5 or 6, which is like, you know, look at that, much faster already. Okay, so this will kind of give us all the connected components, and then now we have to figure out the count of the biggest component. How do we do that? Well, I guess yeah. So I think we just take for number x and a, we just add a count. I think it's fine. C is equal to collection dot default dict of int. I guess actually I use collections dot counter. Counter, and then for x and a, we want it. Okay, so we increment the what we call it, the first find of the first factor. I mean, it doesn't, as long as you take any factor, it doesn't really matter. But but actually, let me cache that so I don't have to calculate the prime factor again, because all you need is one factor. So let's put that in a lookup table. of x is equal to factor sub 0. Okay. And then now we only need to look up of x, and then we do a union find on that to get the union find parent, and then we increment that. And then now we just have to find the max of the counted out values. Maybe that's good enough. We'll see. But I think idea-wise, this should be okay. Implementation is always harder than a little bit, but we'll see. Okay, it would be nice if you told me the answer. Okay, are there any edge cases? What happens if it a sub I is 1? Do I do anything smart with 1? Let's see. And duplicate numbers in general, probably. But I feel like I'm a little bit confident on this one. Okay, well. Oh, because 1 doesn't have a prime factor. Okay, fine. And that's why I test them though, so that's good. Would that cause any issues? Let's see. The only other kind of thing is that I don't do any smart union, but I have path compression, so it should be okay. Okay, let's just submit it. Let's see where that goes. I guess I should have a solution that mixes both of them. But okay, cool. Wow. I'm very slow on this one, so maybe there is a faster way to do this. I mean, I guess I could optimize the prime factor. What I could have done was build a sieve. Yeah, but I think it's kind of running tight on the timing though. So I mean, usually I don't care about timing, but this one is a little bit slower than I would like. And why is memory usage less than 100%? Oh, okay, so my memory usage is actually great. I guess that's what I mean. I guess that's the trade-off. People probably have a sieve or a lookup table for the primes, where I just do not. So I don't. My memory is great, but yeah, not necessarily. And I think there's some stuff that could be optimized a little bit, but I think this is also one of those problems where, at least for Leetcode specific, it's a little weird because you can actually have a global value and you cache a lot of these things so that on multiple tests you take advantage of the prime factor being already calculated for you and stuff like that, which is a little bit dubious versus like each particular case. So like you have almost like a pre-processing cost or something that you use over time. But with that said, and I probably didn't need to do this. I could just have kept track along the way. So maybe that could have been slightly faster, but that part is probably not likely to be the reason. I think the union find is probably, maybe I could be a little bit better about the path compression, but or like doing this in a more balanced way so that the path compression is slightly faster. But 219 seconds, I don't know. Yeah. But overall, if you, if you're following from the beginning to the end, then I'm going to try to explain again. But the idea is that, and I love that, they try to fool you with like these this graph thing when like essentially what I did, and probably is the solution, even though there might be some optimization needed, or maybe that's why people use Java. But yeah. But yeah, so they do expect each node to be like drawn a graph like this. But what I did, as we mentioned before, was I take the prime factorization of each of the numbers and then connect the connect the primes that are in the number instead. And wow, and it did seem like I needed every bit of that speed up. Though I guess I could have just cached this if I was a little bit smarter about it. But yeah, overall not bad. Interesting problem. How long did I end up taking? It took about 20 minutes. I think I spent a good amount of time describing the problem though, so I don't feel that bad. Um, what do I want to say about this problem? I think on this problem again, it is very mathy, so I wouldn't necessarily expect this to be on an interview. There are components that are actually critical to an interview. Notably, connected components is a big thing. I see connected components a lot in general on both sides. You could do it in a couple of ways. You could do it depth first search. You could do it in breadth first search. You could do it in union find. Just know it. I mean, you have to know it. So that part of the problem is very noteworthy. But I would say that the stuff about primes, this is non-trivial, and also like unless you have experience, probably not something that you'll be thought about. It's not very quickly. I mean, it's not impossibly hard. It's just we have 45 minutes to do a programming interview. That's a little bit hard to kind of get into, but it's a code force problem. but overall, a fun problem within 15 minutes, or 20 minutes ish, give or take, which is something that I'm happy about. And there are some optimizations for like pre-calculating, which I did not take advantage of. But yeah, overall, if you're studying for interviews, I would not necessarily use this one unless you feel like you're very strong in math already. But the connected components part, like I said, is worth practicing. But as a competitive programming problem, this is probably like a good hard. I want to say a good-ish hard for normal people problem, but probably like an average-ish competitive programming problem. So yeah, I dig it, and it's good practice. I actually really enjoyed kind of learning the math along the way, and I probably could have done something better. Maybe I should have done a SIF, but anyway, cool. That's what I have for this problem. Actually, let me take a look at this solution real quick. Okay, so we'll skip to I don't know what a DSU necessarily means. Oh, disjoint set union or something. I don't know. But union find is what I usually call it. But people always call it different things these days. Oh, this is what you would call it. Yeah. So all of them too, Factorization, and then okay. I mean, I feel like they really sold the whatchamacallit. Like the intuition is not that intuitive for a lot of people. I feel like this write-up is a little bit like assumes a lot already. But yeah, this write-up already assumes a lot of stuff. I think, yeah, and maybe that's why the rating is pretty low on this solution. But yeah, but otherwise, hope you enjoy my explanation. But yeah, cool.